now we have the final question for 2026, question number 5, which is our unit cell question. Although a little bit different from normal unit cell questions. But let's have a look and see what it's like. So we're giving us a bit of background, and then we've got this formula here with an X and a Y in it, and we're told the oxidation state of copper is +2, and we're asked to define the number of hydroxide ions. So the water isn't going to affect anything, so we can just ignore that for now. And then if the copper is 2+, and the aluminium is going to be 3+, times by 6, and then I've got my PO4, which is going to be 3- times by 4, and then I've got my OH-, and I want to know how many of those I've got. Well, 6 3s is 18, plus 2 is 20, take away 12 is 8, so I must have 8 of these in order to get that back down to 0. So 8 is going to be my number of hydroxides. Then we are asked to determine the percentage copper by mass in the dehydrated sample to 3 significant figures. So in order to do that, we're going to have to work out the formula mass of CuAl6 PO4 4OH8. So it's going to be 63.55 plus 6 times 26.98 plus 4 phosphoruses for 30.97 plus 16 oxygens, which is 16, plus another 8 oxygens, 8 times 16, plus 8 hydrogens, 1.008. So I want to calculate that, which I won't bore you with. But if you do it, it comes out to 741. 741.374. And then I'm asked to determine the percentage of copper. So I do 63.55 divided by 741.374 times by 100. Okay, so if I just do 63.55 divided by that. Oops, 63.55 divided by that. Times by 100 gives me 8.57%. Okay. And then we're given this other substance whose name I can't pronounce. And we're asked to calculate which sample from the table was pure libethenite and which was pure turquoise. So this should be fairly straightforward, so I just need to work out the mass of this. So if I've got Cu2 PO4OH, it's going to be 2 times 63.55 plus 30.97 plus 5 times 16 plus 1.008, which will come to 239.078. And then if I do 63.55 divided by 239.078 times 100, 63.55 divided by that times by 100 gives me that, which isn't any of the right answers. So what have I done wrong? Of course, so this is it's 2 coppers here, so times by 2. So I've times that by 2, I get 53.2%. So that'll be F. So now we need to do the same for turquoise. Let's have a look. Okay. So the water content of turquoise is variable. Y can range from 2 to 8. Okay. So I think what we need to do then is just take this mass and we can add on some water to it. So if I do, so that's the first one. If I do 741.374 plus 2 times 18.008, and if I do 741.374 plus 8 times 18, 2 to 8, right? 2 to 8, yeah, 2 to 8, 18.008. And I see what I'm going to get from those. So 741.374 plus 2 times 18.008 for my water gives me 777.39. If I add on 6 more, I'm going to get 885.438.7. Okay, and then if I do the copper content of each of those, so if I work out 63.5, so 63.55 divided by that one times 100, so that's going to be equivalent to 7.18%. And if I do 63.55 divided by 777.39 times by 100, I get 8.17%. So somewhere between 7 and 8%. So B is our closest answer there. Not exactly right, but I guess close enough. Okay, then we're given some information about chemical analysis. Fine. Then at this point we're thinking, whoa, okay, this is going to be pretty interesting. But unfortunately, we don't have to use these diagrams. This isn't the kind of unit cell question where you're sort of counting atoms inside of unit cells and seeing, what fraction are on the edge, what fraction are on the corner, that kind of thing. It's just a lot of algebra. So a regular tetrahedral molecule shown inside a cube. There. And if you want something extra to do, you can work out the angle there and find that it's 109.5. Just as an aside, but anyway, let's carry on. The volume of a regular tetrahedron. So that's the three-dimensional shape made by joining up all of these corners. It would be a four-sided shape, and we're asked to find the volume of that shape. We're given the formula to do that. So all we need to do is find A here. So how do we do that? Well, let's say that this is X. Then I can say that according to Pythagoras, we have 2x squared equals a squared, right? So that's this length squared plus this length squared gives me that length squared. And now this is also x, so x squared plus a squared, so this one plus this one squared is going to be your diagonal. Okay, and I'm told that this length here, remember this is going to be the P and this is the O. If you're lost at this point, you probably need to stop and read all the question, read everything, all the information it's given you. I'm just assuming that you've got all that information at hand. So this is your phosphorus in the middle, this is your oxygen, and you're told that the PO bond length is 1.54. So x squared plus a squared equals 2 times 1.54 squared. So what I can do then is I can take I want to get A, right? So there's a few different ways you can do the algebra here. I'm trying to think of what's the cleanest way to do it, but I don't want to think too long about this. So what I'm going to do is I'm just going to substitute a squared into here. So I'm going to get x squared plus 2x. I know this isn't giving me the thing that I want. That's going to be 3.08 squared, but it's okay because then I can find if I know what x is, I can find a, I think. So 3x squared, let's just say x squared equals 3.08 squared over 3. If only there was space where they gave you to do the working, right? Okay, so far, and obviously all of this working really should have been in the box, just in case I don't get the right answer at the end, I can still get some marks. So I've got x squared equals 3.08 squared divided by 3. But I know that 2x squared equals a squared. So, what do I do? Let's say we're going to get a squared equals 2 times 3.08 over 3 squared. So a, I should be able to find. So let's try that. 3.08. I think I could make a mistake here. What am I doing? That's not all squared, is it? Let's put it like that. Very, very ugly. Bad maths. Anyway, I'm sure you can follow. 3.08 squared divided by 3 times by 2. Take the root. Gives me 2.515. And all these numbers are in angstroms, so my answer comes out in angstroms. No problem. Sorry about that, it got a little bit messy there, but it should be reasonably easy to follow. So that's A, and then I'm told that the volume of the tetrahedron is, so the volume is 1 over 6 root 2 A cubed. So my volume is going to be that cubed divided by 6 divided by, whoops, no, oh dear, oh no, where am I? Divide by, let's see if this works, root 2, 1.87, okay, 1.87 angstroms cubed, and no tricky unit conversions, unfortunately. That is just the answer. So, then we're told the volume of the unit cell can be approximated as the sum of the volume of the octahedra, tetrahedra, water molecules, and empty spaces. Yeah, it's really unfortunate that we didn't have to use any of these diagrams. It just all comes from the description. Each water molecule contributes an extra 20 angstrom cubed, and the ALO6 octahedron has a volume of 9 angstrom cubed. Calculate the volume of the unit cell in angstroms cubed. Assume the cell is 50% filled by tetrahedra, octahedra, and water. Okay, so let's have a look. So the whole thing is tetrahedra, octahedra, and water, but we don't know how many of each of these there are. We're talking about variscite, and we're told up here the unit cell of variscite is shown. It consists of 8 formula units. Okay, so let me just double check. Variscite is this. Okay, so I'm just going to write that down. AlPO4 2H2O. Okay, and we've got 8 formula units, so we've got 8 of these. Alright, so in other words, the volume is going to be equal to 8 times our the volume of the AL, the ALO6 octahedra, plus 8 times the volume of the PO4 octahedra. Now you don't need to worry about the oxygens not adding up here, because you're told that all of the oxygen ions are shared between 2 polyhedra. So as long as my aluminiums, my phosphoruses make sense, then I don't need to worry about anything else. So this is going to give me 8 aluminiums, 8 phosphoruses, and then I'm going to have to add on 16 times the volume of the water. So I know the aluminium, because I'm told that one there, 9. So this is going to be 8 times 9 plus 8 times the PO4, which is the thing that I just worked out in the last one. So 8 times 1.87 plus 16 times my water one. And each water molecule contributes an extra 20. So 16 times 20. Okay, so that times 8 plus 8 times 9 plus 16 times 20 gives me 407 angstroms cubed. But don't forget, we are told that we should assume the cell is 50% filled by tetrahedral, octahedral and water, but the actual volume of the unit cell is approximated the sum of the octahedral, tetrahedral water molecule and any empty space. So if it's only 50% of that, so that's the volume of the things. So the actual volume, I don't know what, let's call it volume total, is just going to be that times 2. That's by 2. So that's going to give me 814 angstroms cubed. Then we are asked to give the density. So we know the volume. Now we're going to have to do a unit conversion. Great. Okay, so here we go. This is, and if you've done these unit cell questions from previous years, this angstrom to centimetres is a pretty standard unit conversion that we often get asked to do. And we need to know the mass of everything. So what I need to do is work out the mass of this. So that is going to be, aluminium is 26.98 plus phosphorus, which is 30.97 plus 4 times 16 plus 4 times 1.008 for my hydrogens, plus another 2 times 16, 32. Okay, gives me 157. So that is the mass of that, but in the unit cell, this volume, I've got 8 of those, so I'm going to times that by 8. So my mass is 1263.856 grams per mole. Which I can then very easily convert into the actual mass of just this 8 times this number of atoms. So I'm going to divide that by 6.022 times 10^23 to give me 2.099 times 10 to the minus 21 grams. Okay, so that is, this here is the actual mass in grams of 8 aluminiums, 8 phosphoruses, 8 times 4, 32 oxygens, and 8 more of these. That many atoms gives me that actual mass. So now the density is going to be my mass divided by my volume. Now I know the mass I just worked out, I know the volume from up here. All I need to do is convert this volume into centimetres cubed. Well, I know that 1 angstrom is 1 times 10 to the minus 10 metres, which is 1 times 10 to the minus 8 centimetres. Right, because a centimetre is smaller than a metre, so you will have, well, I guess you'd like more centimetres. Well, I mean, this is it. If you're not sure how this conversion works, you need to do a little bit of thinking yourself. I can't think of a good way to explain it at the moment. But anyway, so once you've done that, 1 angstrom cubed equals 1 times 10 to the minus 8, all cubed, centimetres cubed. So this becomes 2.099 times 10 to the minus 21 divided by 814 times 10 to the minus 24. Like that. So divide by 814 exponential minus 24. Which gives me that 2.58 grams per centimetre cubed. And the reason they ask it for it in grams per centimetre cubed rather than, I don't know, grams per angstrom cubed or something like that, is that this number here is a very easy, sensible number for us to imagine, right? So you know that 1 centimetre cubed of water is 1 gram. So you should always be looking to get an answer on that magnitude, okay, on that scale. So if this comes out as like 300 grams per centimetre cubed, it's far too dense, you know, and you know you've made a mistake. Likewise, if you get 2.58 times 10 to the minus 5, this is obviously not going to be true either. Like, we're dealing with a solid crystal here, so we should expect something that's a little bit heavier than water, or a little bit more dense than water, as it were. So 2.58 grams per centimetre cubed is a sensible number to get. Really, it is always very important when you do these density calculations to have that in mind. Just trying to think if there's another way for me to explain this without getting, I don't want to get too much into it. If a centimetre is 100 times bigger than a metre, then the angstrom is like much, much smaller than both of these. But you divide the centimetre up into fewer pieces, as it were. Does that make sense? Oh, I'm starting to confuse myself now. Maybe that's something for a different day. Okay, so far so good. We now are told that, so that was all for variscite, and we're now told turquoise consists of 6 AlO6 octahedra, 1 copper octahedron, and some, phosphate tetrahedra. Some bond lengths, and we're given the volume of octahedra. Assume that turquoise contains 6 molecules of water of crystallization in the formula unit, and the cell is 70% filled by tetrahedra. And then this is the same calculation again, basically. So let's go at it. So our volume is going to be 6 times the volume of AlO6 plus 1 times the volume of CuO6 plus 6. Let's have a look. Hold on. Assume that turquoise contains 6 molecules of water crystallization in the formula unit. Y equals 6. Let's go back. Where are we? So we're given the formula for turquoise here. Okay, so we've got this formula here. I'm going to write that out again. CuAl6PO4 OH8. Because we worked that out earlier. 6H2O. Okay, fine. All right. So we've got 6 AlO6. Okay, that makes sense because I've got 6 aluminiums. Fine. 1 times CuO6. Fine, because I've got 1 copper. So now, when it said some PO4, I know that it meant 4 times the volume of PO4. Because this must just be this as it is, because there's 6 aluminiums and there's 1 copper. So it's 4 of those, plus, and we're told that the hydroxides and the waters have the same volume. So if I have 6 of these and 8 of these, that's 14 times the volume of H2O. Okay, so do I know these volumes? Well, I know that water is 20 angstroms cubed. That's fine. I know AlO6 because I worked that out in the previous part of the question. Where did I work that out over here? 1.87. So that's 1.87 angstroms cubed. Is that right? Part D. No, part D was the phosphorus. It was this one. So it's 4 times 1.87 angstroms cubed. The AlO6. Oh, I was told that this was 9. Okay, so 6 times 9. So that's 9 angstroms cubed. So it's just this. What's this? Right. Well, I'm told that the volume of an octahedron equals root 2 over 3a cubed, where a is the edge length. Now an octahedron is going to be this shape, right? Okay, and you know, if you join up all of these, sorry, my artistic skills not hugely impressive, but if this, assume we have this edge length here is A, then that should give us the we can then work out the volume, but we can double check it because I know that this is 9 angstroms cubed, and I know that the aluminium oxygen bond length is 1.89 angstroms. So that 1.89 angstroms is going to be this bond length here, 1.89. So I can work out A, because that's a right angle triangle there, because that angle there is 90. Okay, so if I do, let's see, I've already done it, 1.89 squared times by 2. Take the square root of that. That gives me A, 2.67. And then if I put that into here, so I cube it, multiply by root 2, divide by 3, yep, there we go, 9. Okay, so it's going to work. So all I do then is I repeat that same calculation with 2.29. So I do, this is now 2.29, I do 2.29 squared times by 2, take the root of that gives me A, and then I do that cubed times by root 2 divided by 3 gives me 16.01. Okay, so then I just go ahead and add everything else on. So I'm going to add on plus 6 times 9 plus 4 times 1.87 plus 14 times 20 gives me 357.5 angstroms cubed, and that's 70%. So the total volume is going to be 357.5 divided by 0.7. 0.7 to give me 511 angstroms cubed. Lovely. And then the final part is determine the density. So in order to determine the density, I need to know this mass here. Look back that I work out that mass anywhere. I've got here. I've got it with 8 waters. So if I do 885.438 minus 2 times 18.008, that's it with 6 waters, I believe. And then I can do that divide by 6.022 times 10 to the 23 that's my mass in grams, and then I'm going to divide it by, it's the same calculation again, 511 times 10 to the minus 24 to give me 2.76 grams per centimetre cubed. Okay, so that bit there, I've not written the working out because it is just the same as this calculation you saw earlier. Again, I feel like that was, as far as unit cells go, there's a lot of reading for this one, which I think is more straightforward than counting up atoms. But I mean, I like the counting up atoms inside unit cells. I think that's a lot more fun to do. This one, it's just sort of getting your way through all this info. So it's a lot of reading and deciphering of the text. But yeah, there you go, done.